Should I get started or?
Yes. Is that you?
So let's go with summarizing where we were so far. So we had we used these bipartite expanders to construct codes. We were able to construct codes with constant rate and linear distance. This one. But unfortunately, most constructions of these bipartite expanders would also lead to codes which are actually not testable in a very, very strong fashion. So just expansion is not going to help us resolve this question of trying to construct codes with constant rate, linear distance, and testable with a constant number of queries. In fact, most of these codes require not just constant, but a linear number of queries to test it. So what we're going to try to do is why do they fail to be testable? So what we try to do, we look at examples of subcodes which are testable, look into the proofs of testability of these codes, and see if we can get some understanding out of them and add this as an extra property to our expander codes to show if they can be made to be testable. This is right now wishful thinking, I don't know, but let's look at, for the remaining half an hour or so, I'm going to look at the example of a few codes which are testable and try to understand why are they testable. These codes are testable, but they don't have, they fail with respect to the other two, one of the other two parameters, either with respect to distance or with respect to rate. So what are the codes that we know that are testable with a sublinear number of queries? There are two classic codes among the codes which we have been talking about. One is the Hadamard code, which we mentioned. This is basically the codes which correspond to the evaluation of all linear functions. And in fact, this is testable with three queries. There's another code, which is the Reed-Muller code, which is the evaluation of low degree multivariate polynomials. It's not testable with a constant number of queries, but it's also testable with a sublinear number of queries. So let's look at both of these codes a little more closely, and let's look at them. Right now, I just defined them as, we defined these two codes in the beginning of the lecture, but let's look at a graphical representation of these codes and see how it fits with the picture we have been seeing so far. So once again, let's recall Hadamard code is a set of all it's an evaluation of all linear functions on the Boolean hypercube. So what's the corresponding bipartite graph representation for this? The Hadamard code has the property that these are the constraints are of the form f of x plus f of y plus f of x plus y equals 0. So you can come up with this sort of bipartite graph in which the left-hand side has the code word indices, which is all strings of the form, all elements of the form. This should be not be n, it's actually 0, 1 to the k, sorry, on the figure, 0, 1 to the k. On the right-hand side, you have all triples of the form x, y, x plus y, and it's connected to f of x, f of y, and f of x plus y. So this is the corresponding bipartite graph. Notice that this graph, previously when we were talking about the bipartite graph corresponding to codes, the right-hand side was always considerably smaller than the left-hand side. In fact, that was what actually gave us the rate of the code. But here, once I describe the Hadamard code this way and I talk about these constraints, I'm throwing in all the constraints. These are far more constraints than required to express the Hadamard code. The Hadamard code, just few of them are sufficient to completely determine the Hadamard code. Most of the other constraints on the right-hand side are actually redundant constraints. But we could draw, one might as well draw this bipartite graph. We could draw this bipartite graph between the code word elements and all possible constraints, which are all these triples of constraints. So this is one natural one. So is there a question or? So we will move to this sort of, we're going to talk about testability of graphs and we're going to testability of certain codes. We're going to move to this representation of the code. We're going to have this bipartite graph representation. Notice once we have this representation, we won't be able to prove rate by showing that the right-hand side is smaller than the left-hand side. We'll have to use some other means to prove the rate. And let's assume that we can prove that these codes do have some sort of non-zero rate, we can prove it by some other means, not by the imbalance of it. We want to use the bipartite graph only to prove distance and testability of the underlying code. So distance will still hold good as long as it's an expander. Distance property will still, you will be able to prove distance of the code. Rate, let's assume we can prove it by some other means. We will now ask, can we actually prove testability of this code? So now that I've described the Hadamard code this way, we can also describe the Reed-Muller code in a similar fashion. Reed-Muller code, you can write it as, and here we just make the simple observation that a Reed-Muller code is, when restricted to every line, it looks like a Reed-Solomon code. Therefore, Reed-Muller code also has this nice bipartite graph representation in which on the left-hand side you have all the elements of, all the code word locations, which is basically all the elements of the vector space f to the m. On the right-hand side, we are going to have a location for every line in f to the m. Therefore, this is basically the point line graph. It's the point lines incidence graph in f to the m. And the right-hand side says the local view of every right-hand side vertex of every constraint should be a low-degree polynomial. In particular, it should be once it's restricted to a line, it becomes a univariate polynomial. Therefore, the restriction of the Reed-Muller code to this particular line corresponding to every constraint on the right-hand side should be a Reed-Solomon code. So this is sort of the bipartite graph. It's a bipartite graph representation for the Reed-Muller code. Once again, for certain settings of M, the number of lines can be far more than the number of points. And this is an imbalanced bipartite graph with the imbalance going in the wrong direction. We won't be able to prove the rate of the Reed-Muller code by looking at this graph. The rate of the Reed-Muller code is proved in a different fashion. But what we would like to understand is, looking at this bipartite graph, can one prove testability of the Reed-Muller code? Just like in the previous case, we wanted to look at the underlying bipartite graph and say whether we can prove testability of the Hadamard code.
Prahladh?
Yes?
So yesterday you said, there are de-randomizations in which the right-hand side can be made smaller. It's still bigger than the left, but is the rate any better, or?
The rate will be, it's going to be the same rate. You're just removing a few redundant constraints. You're just reducing, that's what's happening in the de-randomizations, both for, so the case of, for example, what Madhur's questions was, you don't have to add all triples. For the case of Hadamard, you could just add x, y coming from an epsilon bias set, and x plus the corresponding x supply. You could just add those triples, and that will still be a good test for this one. It just removes a few redundant constraints. The rate, these things don't change the rate, or the code is unchanged in this process. As long as you're only removing redundant constraint, the code is unchanged. And the same, you could do exactly the same thing for the Reed-Muller code. Good. So I'm going to take a slight deviation at this point to testability. Right now we moved from, so previously the local view, we had this bipartite graph view of every code over this one, and we said the local view should be such that all the elements sum to 0. But in the Reed-Muller case, we have a slightly more general setting in which the local view does not sum to 0, but is actually an element of some other code word. It's an element of the Reed-Solomon code word. Let's actually make this a little more formal. So this will give rise to what I would call Tanner codes. So we talked about these codes from bipartite graph, which is this object which I talked about previously. You have a left-hand, you're given a bipartite graph, you can talk about the natural code that arises out of it. So what is it? What's stating here that every constraint over here, we are stating that its local view should be a member of this code even. It should be an even member of the, whatever it sees, every constraint on the right-hand side should see a member of the code even. But this, of course, this seems to be a completely artificial thing. Why should we have worked with the code even? We could have worked with any other code C0. We could have said that every constraint on the right-hand side, the view it sees should be a member from C0. It doesn't have to be this even. So this sort of raises us to the following question of Tanner graph. So here, how I'm going to construct this code is, you've given a bipartite graph as before. G is LRE, and let's assume it is C regular from the right-hand side now. It's regular from the right-hand side. And we are given some code C0 whose block length is C. Then the corresponding Tanner code that arises out of G and C0 is the most natural extension of this, in which I'm going to put all elements X on the left-hand side, so that every single local view corresponding to the right-hand side is a member of C0. Now, to do this formally, we'll have to specify a particular ordering, and according to that ordering, it should be a member of C0. I'm fudging details over here, but for every constraint, we should specify a particular ordering of its neighbors, and according to that ordering, X restricted to NV should be a member of C0. This is what is called a Tanner code. So you give me a bipartite graph and you give me a base code C0, we can lift it up to a larger code C on the left-hand side. This is a natural process. These are also called lifted codes in some contexts. Lifted codes, and what I would like to ask is the following question. Are these codes, the codes, so sort of illustrating what I said. So the Reed-Muller code written in this language is exactly the Tanner code corresponding to the graph, where it's the points line graph, and the smaller code you put is the Reed-Solomon code. So the Reed-Muller code is the Tanner code when you put in the points line graph and the Reed-Solomon code. When you put these two, what you get is the Reed-Muller code. What I want to ask now is there some property of the graph G and the underlying code C0 that makes this corresponding object, the corresponding Tanner code, locally testable? In the case of the Hadamard code, the Tanner, we saw what the graph is, and the corresponding code C0 was the even code. What is the property that makes this thing testable? So let's try to answer this question. We don't yet have an answer to this question. To answer this question, let's go into the proof of why the Hadamard code is testable. So once again, the Hadamard code is this code. We have this code given an evaluation of some function. We want to check if the function is linear or is it far from linear. BLR had proposed a very natural test to check linearity. They just said pick two elements, check and look at the function at these 3 points x, y, and x plus y, and accept if f of x plus y equals f of x plus f of y. And they showed this amazing property that if first thing, it's easy to see that if the code is linear, if the function in fact is linear, it's going to pass this test with probability 1. And the amazing thing about this test is if the function is far from linear, then it's actually going to pass this test with very small probability. Or the contrapositive, if the rejection probability of the function is very small, then the function is actually going to be close to linear. Let's just formalize whatever I said now. So let's look at the rejection probability of a function. Given a function, let's find out what's the probability that this test fails. This is exactly the probability when I pick a random xy, f of x plus y is not equal to f of x plus f of y. And let's look at the distance from linearity. Let's look at what's the closest linear function to this given function, and let's look at the distance of the function from linearity. What BLR prove is a statement of this form. If the rejection probability is small, then even the distance to linearity is small. That is, if the test passes with high probability, then it must be close to a linear function. So how does one prove this theorem? So I'll spend about the next 5 minutes or so trying to prove this theorem, and in the property, while doing so, we will see that the underlying graph has some additional properties because of which this theorem actually goes through. Okay, many of you might have seen this. This is a very classic theorem. Many of you would have seen this proof, but I will sort of do it from scratch again, just to show that there is something out here which says that the underlying graph has some extra features which make this theorem go through. Once again, what we want to show is we're given a function f and we're told that the rejection probability of the BLR test is very small. Then we want to show that actually this corresponding function, its distance from linearity is at most twice the rejection probability. So this is what we have, and we want to prove this. And how does one typically go about doing this? If you haven't seen this, this is a beautiful proof due to Prahladh. And the proof goes this step. First, we try to come up with the candidate closed linear function. We come up with this function g, which is sort of so you find for every x, you find out what do the other y's vote for x. Basically, you look at f of x plus y minus f of y. This is the vote that y says x should be. If it were linear, this would be exactly f of x. So g of x is the majority, is the majority vote given by all the y's. We define this function g of x. And then the proof of BLR goes in just 3 steps. It first shows that this function g that we have defined is actually close to f. It's at most twice the rejection probability of f. That's the first claim. Second claim shows that the way we have defined g, we have defined g to be the majority value of the votes. For every x, we define g to be the most, it's a majority value. We'll show that it's not just the majority value, it's actually an overwhelming majority value. That is, if the rejection probability is not too large, in fact, if it's less than 1/6, then for every x, not just most x, for every x, g of x is not just the majority value, it's not just greater than half, it's actually greater than 2/3. That is, majority value is actually an overwhelming majority. We'll show this. And then given this, we'll prove the next claim that g is actually a linear function. Now, once we have claims 1, 2, and 3, actually just claims 1 and 2, 1 and 3 will now suffice to show that f is close to a linear function. So how do we go about proving this theorem? So I'll actually go through each of the proofs, each of the steps in the proof. So that's actually here's the note. Have I moved to the note or is it?
Not yet.
No?
Yeah.
Yeah. So if you'd like to prove the first of the claims, claim 1, I want to prove that delta fg is less than or equal to twice rejection of f. Let's recall once again what's the definition of g. G is the majority vote that every y gives. So the proof of this, how does one prove this? So let's define the set bad. So let's define to be those elements x such that whose majority it's those elements for x for which this happens with probability less than half. Let me write this in a slightly different fashion. Which f of x is not equal to f of x plus y minus f of y. It's less than half. Be clear that if x does not belong to bad, then in fact it is the case, the way bad is defined, then g of x is equal to f of x. The majority value agrees with f of x. The way bad is defined is whenever x doesn't belong to bad, g of x squared. This implies that basically that delta f of g is always less than or equal to the fraction of bad elements. Now what's the rejection probability of f? The rejection probability of f we know is exactly probability f of x plus y not equal to f of x plus f of y. This is at least the probability that the x I pick, x is in bad, times the probability that f of x is not equal to f of x plus y minus f of y given x is in bad. This one is equal to mu of f, mu of bad, and this quantity by definition is half, is at least half. And that gives us the whole.
Did you define bad backwards? It's greater than half.
Did I define bad backwards? Yeah, I defined bad backwards. So this yeah.
No, bad is good.
Okay. This is not the. Okay, let's go to this claim. Fine. Let's go on to the next claim. The next two claims are the more. claim, we want to now show actually that if rejection probability of F is less than 1/6, then for all x, g of x, which was defined to be the majority value, is actually not just the majority value, it's an overwhelming majority value. So by definition, this expression is at least half because it's a majority value. What I want to say, it's not just majority value, it's an overwhelming majority. Actually, let's defer the proof of this claim. We'll prove, given this claim, we'll prove the next claim and then come back to this claim. We want to, we have claim. We want to prove the third claim. We want to show that G is linear. How does one prove this? What do I want to show? To prove this, I need to show that for all xy, I have the property that g of x plus y equals gx plus gy. One needs to prove this fact. Now let's fix any xy. One, gx can be written, we know it is, so gx can be written as say fx plus z minus fz. This happens at least 2/3 of the time by claim 2. For a random choice of z, this happens 2/3 of the time. Gy is fz minus fz plus y 2/3 of the time. This happens with probability at least 2/3. This happens with probability at least 2/3 of the choice of z. G of x plus y is f of z plus y minus f of x plus z with probability at least 2/3 of the time. Now if you sum all the three equations, you get 0 on the right hand side and you get the required thing, and that's something which happens with probability strictly greater than 0, and hence it should be, if it happens, there is some z that witnesses this, so this is true for every single x and y. For every x and y, for every adversarially chosen x and y, there is a z which is going to witness that g of x plus g of y is g of x plus y. The fact that it's an overwhelming majority lets us prove this. So we sort of, to show this sort of condition over here, we are using another element z, which is sort of coming from the overwhelming majority to show that g of x plus y equals gx plus gy.
I guess you
Actually,
can strictly bigger than 2/3.
Yeah?
Yes.
I didn't catch.
I think you need strictly bigger than 2/3, otherwise the.
Yeah, sorry, I do need bigger than 2/3.
No, in the bottom. Yeah, these guys.
Yeah, bigger than 2/3. Yeah. Sorry, thanks. So one can prove this claim. So what I want to say is, while proving this claim, somehow to show this worst case condition, want to show for every x we needed g of x plus y equals gx plus gy. We use the z which came from claim 2 to show that there is most z's, not just most z's, 2/3, more than 2/3 of the z witness the fact that g of x is equal to f of x plus z minus f of z. The same z witnesses f of z minus f of z plus y. Therefore, there will be one z that sort of witnesses g of x plus g of y equals g of x plus y, and that's enough to conclude this fact. So what does this tell us? If you now sort of go back to the picture which we had. Is it still in the note or has that shifted to the?
It's the note. Oops.
taking me longer. This tablet, I'm using this tablet the first time. Back to the slides.
Yes.
Okay, so look at the proof of this one. So implicit in the proof, so this claim 3 basically said, so I wanted to prove this, we had this bipartite graph between the code, the 0, 1 to the n and 0, 1 n cross 0, 1 n. This was sort of defining the constraints of this one. So even though the actual test was between this, while proving the Hadamard code was testable, we actually had this third layer which consisted of these, it came up with these z's. It was talking about x, y, z. So it's this, the second layer is looking at x, y, x plus y. The third layer is looking at these sort of, is going to look at x, y, x plus z, z plus y, x plus y plus z. It's going to look at those constraints. And it's a fact that this extra layer exists is what actually makes the local testability proof go through. And if you look at it now, if you look at this graph, this underlying graph, this one, so I'm going to, this graph is a high dimensional expander the way we defined last time. That is, if you look at the edges of this, this is exactly going to be a high dimensional expander. So it seems as if even though the way the proof of testability used only the edges, even the Hadamard code was defined only between the first two layers, we used this extra, the third layer, to actually prove testability of the corresponding Hadamard code. So there was this underlying implicit high dimensional object over there, which sort of helped us to prove testability of the Hadamard code. And this is not just the case of the Hadamard code. For instance, if you also go to the proof of the Reed-Muller code. So for instance, if there's a proof of Reed-Muller code due to Raz and Safra, in which, or even Aurora and Sudan, in which you want to, the Reed-Muller code is defined by this bipartite graph between the points graph and the lines graph. What the intermediate step in the proof talks about a planes graph. It builds up this in three-layered object and uses this three-layered object to prove testability of the Reed-Muller code. This is one of the proofs of way in which Reed-Muller is, the fact that Reed-Muller code is proved is this is one of the ways in which we know how to prove Reed-Muller code is testable. There are other ways in which you don't have this third layer, but it so happens in both these proofs, it's implicit in the proof that you actually, even though you just had a two-layered graph, an expanding graph, which defined the code, while proving testability, you built this three-layered graph, which was a high-dimensional expander, and used this to prove testability of the underlying object. So given this, it's natural to ask if the code that we were defining, the code that we had some Tanner code, if the Tanner code is actually part of a high-dimensional expander code, high-dimensional expander, does that make it easier to prove testability? In other words, what we want to ask is, we had defined this Tanner code this way, and to ask if this graph G was actually, if this two-layered graph was actually part of a three-layered object, or some other object which has some high-dimensional expander property, then can we show that this corresponding code is locally testable. Notice that once it's part of this larger object, the sort of the reasons for, we were able to show that expander codes are not testable, and there were some, that's basically because we were showing that the code had a lot of, even though it violates there are code words which are far from the code word, but which don't violate a lot of low weight code words. Once you have this sort of three-layered object, that sort of disappears. So the question is, can we actually make this one? Because underlying in both these proofs of testability, there seems to be an implicit high-dimensional object. And is this sort of coincidence, or is it actually, can one show that if there is a high-dimensional object, if the code is defined by a graph which is part of a high-dimensional object, can one prove local testability of the underlying code? What one can show, there are some preliminary results if the underlying high-dimensional object has extremely good agreement testing results, the way I stated with yesterday's lecture, then one can in fact prove such a result. But of course, these are extremely strong agreement testing results, so strong that we don't know how to prove them, and for all that we know, they might be false this one. But one can in fact show that if you have such a high dimensional object, then there is an underlying agreement testing theorem, and one could use that in principle to prove local testability of this. And sort of this has been sort of an intriguing question for a while, and actually this is what I wanted to talk with. So it was asked, so we had this notion of expanding codes, expanders gave rise to codes. They gave rise to fantastic properties of codes, but the very same fact that it was expander failed to be showed that just expansion is not sufficient to prove local testability. In fact, expansion makes it not locally testable. Question is, most proofs of local testability seem to underlying use this high dimensional object. Can we actually make this more formal? Can we actually show that if the Tanner code comes from a high dimensional object, can we show that the underlying code is locally testable? It'd be interesting to show this, and I think there is a high dimensional object lurking in the proof of testability. It would be good to answer this question. Talk with this.
Okay, thank you. So, any more questions?
So in these algebraic codes, basically there is a very, in the big picture you have of these checks, right? There are really a lot of checks which somehow end up having still very low rank, so the code has decent distance.
Yeah.
And is there a framework of Tanner codes where you can make the right-hand side much bigger and yet the code is non-trivial?
Yeah.
So that seems
So I have been talking about, so far I've been only talking about testability. So the question you're asking is, if you put the right-hand side so large, why does the rate even survive? Why does the rate completely disappear? The rate could just, the only code that satisfies all these constraints could be the all zeros code word. So the smaller code C0 should talk well with the graph to actually, for example, even if you took the planes point graph, only if you put the Reed-Solomon code word are you going to get the Reed-Muller, a nice code word. You couldn't have put any other code, smaller code over there and expected some rate. In fact, most other codes you put there, the rate is going to get completely killed and you won't get anything. So there's the other question of, are there codes for which rate survives? I don't know this. So they might, so you need a C0 which talks well with the geometry of this object. So if you're going to build these high dimensional expanders from some nice number theory or something, it might be the case that there are C0s which talk well with it and rate is preserved in it. Just the way you show Reed-Muller codes have nice rate. So that's an alternate question. We also need to, right now I'm showing that if rate is preserved, then the underlying code possibly is locally testable. I don't know how to prove that rate survives at all after this process. But just like in the case of, this is all wishful thinking right now, just like in Reed-Muller codes, the Reed-Solomon code, for the points line graph, the Reed-Solomon code is a nice smaller code that talks well with the geometry of this graph. We need a C0 which talks well with the geometry of the corresponding high dimensional expander graph.
But I mean, if you think of, on the other hand, C0 of constant size, then you can as well think of it as parity check code, right? You'll just lose a constant factor of the soundness. So that will sort of take away C0 from the picture. It will just be...
Yeah, if it's going to be constant size, it's going to take away C0 from the picture. That's true. Yeah.
But do you know, like even for Reed-Muller, how do you prove that there is rate? I mean, do you know a proof where you just look at the constraints and you show that they have low rank or something like that?
I think some of these lifted codes work this way. I mean, these lifted,
Don't they work by demonstrating code words?
Yeah, they do. They work by demonstrating. I mean, the hard thing there is, so they sort of do the opposite thing. The testability or decodability is by construction and easy. I think the hard work is to lower bound the rate.
Right.
And they kind of basically show that some monomials survive.
Yeah.
Yeah.
So that's not the same as showing that the constraints are in low rank. Okay, I mean
it's the same, but yeah, the methodology is different. It does exploit that difference.
Yeah, that puts the focus on the other. It shows, firstly, all these lifted codes at least have the Reed-Muller code. What they want to show is rate is even more number of, the rate is actually larger than the Reed-Muller code. They want to show even more things survive. And that the hard work over there is trying to show rate survives. Here I'm assuming there are codes for which the C0 speaks well. And I'm hoping that a similar proof might show local testability. So, yeah, it's just asking, is it coincidence that in both these proofs, the underlying object actually is a high dimensional expander, or is that coincidence that these two locally testable codes which we've been using so often have this high dimensional expanding object lurking underneath.
Any more questions? Suggestions? Okay, thank you very much then. We hope to see you on Monday.
In person.
I got my visa. Yeah, should be there soon. Yeah.
When do we resume?
Okay,